Well, good morning. I'm Saied Saiedi. I'm with Bergmann Associates, an engineering firm headquartered in Rochester with many offices in many states, including strong presence and growing presence in Ohio. I'm reporting on a fast-tracked shore protection project along Lake Michigan. I'm acknowledging the contribution of my co-authors, James Ensing and Michael Leonard, both project managers, and I'm happy that James is here and he's got my back. This is the record of the water level variation in Great Lakes in the last 100 years. Of course, lots of ups and downs. In particular, quite recently, in the last 3, 4, 5, 6 years, depending on the lake, we are dealing with a rising water level, I would say, in most of the lakes, including Lake Michigan. Lake Michigan is here, starting from 2012, 13, Lake Ontario, again the same thing. We're talking about significantly higher water level compared to the long-term average. This, coupled with some climate change thing and stronger wave storms, have led to damages to many structures along the shorelines of most of the Great Lakes, including Lake Michigan. Another example and another project we are dealing with as these days is Lake Ontario in 2016, April, and again 2017, late March and April. Again, lots of storms and damages to many structures, including a few barrier bars. In this particular one, this is Port Bay, New York State, and as you can see, top right picture, there is this navigation channel in the middle and a west barrier bar partly protected by rock. East barrier bar has been broken a couple of times. Here is the bay fed by many streams, and here is the lake. You can imagine the consequences for both optically, psychologically, and also structurally for people and residents along the shorelines of this bay. Some of the implications being, of course, the damage, debris, sediment intrusion into the bay, impact on the inhabitants, and lots of other things. Same issue in one of the locations along Lake Michigan. St. Joseph, St. Joe, you have the river coming into Lake Michigan. This is St. Joe, Lake Michigan River, port, and north is that way. This is the water department for water supply, purification of water. And starting from perhaps 60, 70 years ago, the traditional protection of the shoreline was steel sheet pile or bulkhead anchored to steel beams, rows of them, and anchored using rebars. And in some locations, depending on the importance of the structure, the designers or the owner they decided to have normal to the shore sheet piles as well. And this is an example of the along shore sheet piles together with some sort of sheet piles or groins normal to the shore, and the row of steel piles, anchors, and sheet piles. This is the undamaged steel sheet piles. In one of the locations, and by the way, along this part of the lake, you've got, of course, residents, and you've got a railroad, and you've got the bluff, and these are the sheet piles there. About 20 years into or after the construction of the sheet pile and this particular location, signs of erosion, some because of the stormwater from the land and some from the wave attack. 2017 in particular, it got worse. The damage or the removal, destruction of the sheet piles, removal and disappearance of the ripraps, and even erosion of the bluff, and putting the railroad at risk, and residents worried as well because part of the land is shared. It's some sort of easement arrangement with the residents. And interestingly, this particular picture was taken by one of the residents who was very interested, of course, for obvious reasons. When we were asked to help the client, the major stakeholder of the whole structure, it was early June, and the decision was because of the incoming and growing risk to the whole bluff and to the whole railroad and to the whole area, the mandate was to do things very fast. As we call it, early contractor involvement, at the same time working on the design, at the same time thinking about the permitting, everything. We did it within 2 months. I'm talking about the design, permitting, and procurement of the contractor, and doing some preliminary work, 2 months, June and July. And the purpose was to finish the construction, of course, before the winter. Then we had a window of 2 months altogether for the construction. Of course, lots of efforts and meetings and construction management issues, the whole team. You can appreciate the size of the waves in this picture. Views of the damages, talking about the destruction of the sheet piles. Some part of the sheet piles gone completely. Again, another view of, in some locations, because of the damage, they decided to have a second layer of steel sheet pile, and that gone. The beams and the steel piles are, of course, there. What we did, of course, together, among many efforts, going to the site investigation, land survey, walking inspection, doing the topo survey and bathymetric survey, learning about the beach and bathymetry in particular, because one of the questions was why this particular location. Of course, no one knows for sure, but sometimes it's because you are dealing with a particular geometry for the beach. Depending on the geometry, you may have some sort of concentration of the energy of the wave at a particular location. It could be non-uniform construction things, foundation. We looked into those things as well. Typical undamaged section is the bluff slope of one to 1.5, fairly steep. And then the sheet pile, and behind it riprap, and then the beach slope about 20% typical. And then the damaged section, the sheet pile gone, the bluff significantly eroded. That's the typical section. Investigation into the water level variations, the choice for the maximum water level, the design water level, the upper limit of the structural protection, the lower limit, those design things. Looking into the wave statistics. For that particular location, the wave statistics started from 1960 to present, about 50 or 60 years of statistics, good statistics, many stations looking into the statistics to come up with the design wave height. Of course, the easiest way is to find out the maximum wave height, both actual and predicted, 50 years, 100 years, to decide about H max, like in many occasions in oceans and big lakes. You assume sort of statistical distribution for the waves, Rayleigh distribution. Based on that particular distribution, your significant wave height, so-called significant wave height, is H max divided by 1.86 roughly. You can live with, and you can do with it. And then again, for many of the coastal protection things, the design wave height is either the height of the breaker or the average of the top tenth of the waves when you sort them. Going through the statistics, and interestingly, like in many actual projects, if you want to be good and fair to the design and to the client, you shouldn't be relying on the theory, on the formulations alone. We spend a lot of time going to the field, looking into other structures in the area to learn about, to see which structures withstood the test of those big waves. Look into many of the reports and many properties. We were looking in particular about the actual evidence of the damage or the record of the big waves on some of the structures. We did find a few good information. This is a comparison of actual extreme waves in the last 5-6 years compared to the predicted 100 years wave. Very, very close. Just look at the numbers. 100-year wave, 25 feet. Actual, 21 feet. By actual, we're talking about the waves that happened a few years ago, which means things apparently have changed, mainly because of the water level rise and also storms. Doing the calculations for the design wave height, in brief, the design wave height, that's the deep water. It was about 11 feet. And the decision was to go with the rock revetment. One of the major things we decided was, instead of removing the whole damaged structure, we decided to let them stay there. The remains of those piles and steel beams and the steel piles, they have withstood about 70 years. Of course, we got rid of some of the bad pieces or the garbage pieces. We decided to leave them, to embed them into the new structure for two reasons: to save cost and also to rely on the role of, they can play some sort of role in terms of interlocking with the riprap and the rocks. and it was successful. This Hudson equation, empirical theoretical equation, is basically comparison of the energy of the wave, which is the numerator, with the weight of the necessary structure, and the average rock size ended up to be about 4 feet or 5,000 pounds, about 2.5 tons. Of course, when you decide about the average, you've got some range, maximum, minimum. This was the theory. The result, of course, it was some sort of surprising to the client. It was about 2 or 3 times bigger than the size of the existing riprap. And again, you've got to be kind and you've got to understand the concerns of the client. It's not good enough to show them a bunch of formulations. What again we did, we presented evidence of some of the structures and rock revetment in the area that withstood the waves. We went to the field. We showed them the evidence of the failed ones and those who decided to repair. Some of the pictures belong to New Buffalo in the area, not very far from St. Joe. And another evidence was a few miles. I'm talking about this particular one. And the water department, a few years ago, they had the same issue. They decided to have a rock revetment. We showed the client that they have done better in the last few years, and look at the size of the rock in the structure. And that had an important role in convincing the client to go with the large rock size. Typical design, construction. This is during the construction, barge, crane, and clamshell. And of course, you don't see the part of the rock riprap which is submerged. This, we didn't do any steel sheet piling again. Again, one reason was cost, another was time. Another, we decided that by increasing the size of the riprap, we don't need to have those steel piles anymore. You've got the old steel piles there, sheet piles there, sheet piles there, no sheet piles there, and we restored the bluff as well with crushed stone. The quarry, about 3-4 hours from St. Joe. Quarry. And the construction and our role, Bergmann, we provided construction administration services, preparation of the bid documents, response to contractors, review of construction submittals, and monitoring the progress of the construction. Everything construction, again, 2 months. By November 10th, 2017, everything was ready, and we're happy to say that in the last few months and a few storms, the structure held. May I ask James if you could speak to the permitting, please?
Sure, Saied. So on the permitting side of things, obviously the client had requested basically a fast tracking the project and getting it done that year. As you can see, the access to the site with the bluff was all going to be by barge, and bringing a contractor in early, they couldn't guarantee that they could be out on the lake after November 1st due to ice and whatnot. So we knew we had to fast track it. We worked closely with the MDEQ in the state of Michigan. And then because it is waters of the U.S., the Corps of Engineers was also involved. One of the sort of Saied talked about a little bit, we came up with design calculations that showed quite a bit more armoring than was typically designed for and installed in that area. And we got a lot of pushback from the Corps of Engineers, even though we're using their methodology to design it. But And they're like, well, what's going on? How come no one else is putting the riprap that far out and that deep into the lake? And eventually, we actually had to scale it back a little bit just to get the fast track the permit.
And we dealt with two authorities for the work permit. One was the U.S. Army Corps, and another was the soil.
Yeah, we had to get a soil erosion permit at the county level.
Right.
That was fairly straightforward.
Right. Okay. Thank you so much. And talking about the extent of the riprap, I forgot to mention this. The beach slope about 20%, and of course you've got to go offshore. The design, the lowest level for the water level, which was about 6 feet vertical below, and plus 1 wave amplitude down, which takes you again offshore. And for this particular structure, because we were worried about, we didn't know much, we didn't have time to study underwater that much in terms of the foundation or the geology of the beach, we decided again to extend the riprap again further because of the possibility of the toe erosion. And that was why it was a bit of concern for the permitting side of it. And altogether, a very important project, protection of very important structure, lots of stakeholders, the whole thing since first day till the end of the construction and commissioning, 4 months. And we were happy about the performance. Thank you so much. If there is any question.